So we will continue talking about the cache. We want to measure the cache performance, and after that, try to find a way to improve this performance. We know that the components of CPU time are the program execution cycles, which includes the cache hit time and the memory stall cycles. And this is mainly from cache misses. So with simplifying assumptions, we will say that the memory stall cycles are the memory accesses divided by the program, which means that I'm getting how many accesses that I'm having in a code or in an assembly code. This is multiplied by the miss rate, multiplied by the miss penalty. We can see that we could define the miss rates as we've seen before. They are the number of misses per instructions. And at this point, we can measure the performance by knowing that the CPU time is actually the instruction count times the CPI times the clock cycle time. However, because we have memory stall cycles, now the CPI, this would be the base CPI or the ideal CPI, and we add to that base CPI the memory stall cycles. And this one, we call it the CPI with stalls, or sometimes we call it the effective CPI. Now, these memory stall cycles, they come from cache misses. And they are a sum of read stalls and write stalls. So if we calculate the read stall cycles, you need to know how many reads you have in a program. You multiply it by the read miss rate, and then you multiply it by the read miss penalty. For the write stall cycles, you do the same. The writes, how many writes you have in the program, you multiply it by the write miss rate, multiplied by the miss penalty. And you could add to that the write buffer stalls if you have a write buffer. Now, as an example to understand what we've said, if you were given two caches, one for the instruction and one for the data, and we assume, or you are given that the instruction cache miss rate is 2%, and the data cache miss rate is 4%. You are also given that the miss penalty is 100 cycles. The base CPI, or what we defined as the ideal CPI, is equal to 2. And you were given that the load and stores are 36% of the total instructions. So we organize this given information in a table. As you can see, the miss rate for the instruction cache is 2%, for the data cache is 4%. The miss penalty is 100 cycle in both of them. And the access percentage for the data cache, it was given clearly in this line that it is 36%. And this is because you have load and stores that contributes to about 36% of your code. Now, for the instruction cache, you always load from the cache instruction by instruction sequentially. And this is why the access percentage is 100% and the base CBI is 2. Now you need to know how many miss cycles per instructions. For the I cache is 100% times the miss rate times the miss penalty. So 2% times 100, which is equal to 2. For the D cache, you have 36% times 4%, which is 0.04, times 100 cycle, which is 1.44. So the actual CBI is the base CBI, which is the 2, plus the additional miss cycles per instruction, which is this 2 plus the 1.44, and the total would be 5.44. So if you compare this amount, which is the effective or the actual CBI, to the base CBI, and you get the ratio, you can get the speed up or the slowdown, and you can see that the ideal CPU is 5.44 divided by 2, which is 2.72 times faster than the actual CBI. So we are telling you here, because of the miss rates and the miss penalties, now the CPU performance is getting worse. There is another way to measure the cache performance, which is by calculating the average access time. The point here is that the hit time is also important for the performance. And to get the AMAT, or the average memory access time, you say that it's equal to the hit time plus the miss time. And the miss time is actually the miss rate times the miss penalty. And this is a quick example. If you have a CPU with 1 nanosecond clock, the hit time is 1 cycle. And usually this is the case. If it is hit, you take 1 cycle to get the information, that's it. If you have the miss penalty 20 cycles, and the miss rate for the instruction cache is 5%, then the AMAT is equal to 1, which is the hit time, which is 1 nanosecond, plus the 0.05, which is the 5%, times 20 cycles. So you see that you need 1 cycle for a hit time, and you need these many cycles, which is 0.05 times the 20 cycles, and you get 2 nanoseconds. And as you can see, you have in the hit time 1 nanosecond, and for the miss time, you will spend another 1 nanosecond. So the total of the average memory access time is 2 nanoseconds, which means right now you will take 2 cycles per instruction. So previously, if you consider only the hit time without worrying about the cache performance, you would say that you will need only a single cycle to finish. However, because of we need to worry about the cache performance, the real average memory access time is actually 2 cycles. 1 cycle is the hit time, and another cycle because of the miss. Now, as a performance summary, when the CPU performance increased, the miss penalty becomes more significant. Decreasing the base CBI, this is good. We need to decrease it as we need to decrease it to the best we can. The greater proportion of the time actually spent on the memory stall. So to decrease the CBI, you need to decrease memory stalls or remove them all together. Increasing the clock rate, the memory stall accounts for more CPU cycles, actually. You can't neglect the cache behavior when evaluating the system performance, and this is the bottom line. We need to always worry about the cache performance when we evaluating system performance. So now we will see the different caches type. We have the fully associative cache. We have in-way set associative cache, and we have the direct map cache that we've described before, which is also a one-way set associative cache. So actually, these two types are the extreme ends. And in the middle, we have n-way set associative cache, and based on your choice of n, you have many shades. You can have two-way set associative, four-way set associative, eight-way set associative, and so on. So you start from the direct map, which is one way, and then you increase the n by power of 2 until you reach to the fully associative cache. These are the types that you can have for associative. Now, the fully associative cache, a block can go in any cache entry. In the n-way set associative cache, each block belongs to a certain set, and each set contains only n entries based on what you assumed. For the direct map cache, each block is actually mapped to a single entry because you can find its address using the formula that we've taken before, and we are repeating this here. Now, in the full associative cache, the whole cache is a single set. In an n-way set associative cache, you need to know how many sets you have. Or specifically, if you have a block number, you need to determine which sets should take this block. And to get this, you can find it using this formula. The cache set number is equal to the block number modulo the number of sets in the cache. For the direct map, the block number, or what we call it, the address, determines which entry. And the cache address number is equal to the block number modulo the number of blocks. Now, the fully associative cache requires all entry to be searched at once, which means that you need a comparator for every entry, and this is expensive. In an n-way set associative cache, you need to search all entries in a given set at once. So this is limited by how many entries you have for each set. And because of this, you need n comparator, which is less expensive than the fully associative cache. For the direct map cache, you actually have only one choice. And you don't need to search anything. You directly go to that choice by knowing its address using this formula. And because of this, you don't have to add any comparator. To understand this better, in this slide, we have a direct map cache, a set associative, and a fully associative. And this, or in all three of these caches, we assume we have 8 entries. So we have 8 entries here. Similarly, we have 8 entries here, and we also have 8 entries here. But the way we manage them is different. So in a direct map, we know that we get the cache address number by knowing what is the block number. So if you are looking for block number 12 in this cache, we know that the blocks that we have only start from 0 to 7. So we get 12 mod 8, because the cache size is 8, which is equal to 4. So you know that goes to the fourth position of the direct map. Starting from 0, you count 0, 1, 2, 3, and this is the location that you need to put your block on. In case you are writing. If you are reading, then you need to search for this block, and to search, you simply get the address using this formula and directly you point to it, and you don't need to search. However, if you take a set associative, now the set associative that we chose here is actually two-way set associative. Two-way set associative means that for every set, you have two locations. For this set, you have two locations. For this set, two locations. And for this set is also two locations. Now, if you have the same block address, so to get the cache set number, now because we have 8 entries, and we need to design a two-way set associative, so we will have 4 sets this way, and each set will contain 2 entries. So if the block address is 12, you say 12 mod 4, because now you have 4 sets, and this is equal to 0. So it's in set 0, and you have 2 locations. If you are writing a data into the cache, either you choose this place or this place. Both are equivalent because they are contained by the same set. Now, if you are trying to read the cache, you search for the first. If it's not there, then you go to the second. And here in our example, it's there, and you get it. And that's it. So notice that we searched 2 times because it's two-way set associative. Now, in a fully associative, you have only 1 set. And basically, you can store anywhere. This is actually chosen random. We store right there. And if you want to read, you have to search the whole cache. So you search here, and then here, and then here, and so on until you find it. So in the worst case, you would search the whole cache if it is in the last place. Now, to understand the spectrum of the associativity, for a cache with 8 entries, this is similar to the example that we just seen. So a one-way set associative, or the direct map, you will have it this way. So you have blocks from 0 to 7, and you should store the tag and the data. Now, for a two-way set associative, this means that for each set, you will have 2 entries. So for each entry, you will store the tag and also the data. And they are equivalent. Either you store here or you store here. And if you want to read, you should check this one, and then you check this one. So you check 2 of them. Now, as we go, or as we increase n in the associativity, this is 1 way, and then we move to 2-way, and then we move to 4-way. Now it's that we are jumping in power of 2. Now the number of sets will be divided by 2. So here we have 4 sets. Now we have only 2 sets. And for each one of the sets, we have 4 entries. And this is why we say 4 ways. We have 4 entries. Each one of them has a tag and a data, as we explained. And now if you want to search for one of them, if you are trying to read a certain address, then you check this one. You check the tag in the address with the tag stored in the cache. If they are matched, then it's the data that you're looking for. And you need to check all 4 entries until you get the one that you need. In the worst case, it's going to be in the last one, so you need to search 4 times or look 4 times. Now, if you increase it 1 more times, 8-way set associative, that's the next power of 2. In the 8-way set associative, you will divide the number of sets by 2. So you have only a single set, which means that this is a fully associative cache where you can store anywhere of the cache. And in the worst case, you need to search 8 times. Now, let's look at an associativity example. And we are comparing 4 block caches. So you can notice in direct map, we have 4 blocks. If we have 2-way set associative, then we'll have 2 sets, and each one of the sets have 2 locations. And if you have fully associative, then you have a single set, and you can store anywhere. Now, the block access sequence, you want to access block 0, followed by block 8, followed by block 0, followed by 6, and then 8. And this is why we list them this way, as you can see. The first thing that you should do is find the address. And to find the address for the direct map cache, you get the cache index by getting the block address mod the number of the blocks. We have 4 blocks, so you say 0 mod 4 is equal to 0. Similarly, 8 mod 4 is equal to 0. 0 mod 4 is equal to 0. 6 mod 4 is equal to 2. And 8 mod 4 is equal to 0. And now what happens? These are the indexes of the cache. So if you want this address, you go to number 0 and you store the content of the address 0. This address. So it was a mess. Now the next one is 8. Originally, what you had is the content of the address 0. It's not 8. So it's not there. It's a mess. You take it out. You take out the 0 and replace it by the 8. Now, at this point, you access 0, which you were storing before, but you already replaced it. So at this time, it's mapped to the same place in the cache. So it's a mess, and you take out the memory contents of address 8, and you put memory content of address 0. So it's a mess. Now at this point, we have 6, and the cache index for it is 2, so it's not 0 anymore. It's somewhere else. It's in 6, but it was empty before, so it's a mess. And at this point, you want the block address 8, and unfortunately, last time we had 0, so we override the 8 and we make it 0. And because of this, we don't have a hit. It's a miss, so we take out the 0, and in place of the 0, we overwrite it by the content of the address 8. So in conclusion, using the direct map cache, all of them were misses. All of these accesses, the 5 accesses, they were all misses. Now the 2-way set associative, you first get the index, which is the set index, which means in this, for each block address, where do you go? Set 0 or set 1? So in these cases, since we have a 2-way set associative, and you have 4 blocks, you will have 2 blocks for set 0 and 2 blocks for set 1. So basically, the number of sets that we have are 2 sets. And because of this, you take the block address mod 2, which is equal to 0, 8 mod 2 equal to 0, 0 mod 2 is equal to 0, 6 mod 2 is equal to 0, and 8 mod 2 is also equal to 0. So they are all mapped to set 0. Now what happens at the beginning, you have this access, so you put the content of the memory there, followed by 8. So now you don't have to overwrite the memory 0 because there is another location that is empty, and you put the content of the location or the address 8 in this location. Now you are accessing 0, but luckily we didn't overwrite it since we have more space. And this is the advantage of the associativity. And because of this, we were able to access mem0, and it was a hit. Now, at this point, we have 6. The block address is 6, and it was mapped to set 0. But at this point, we have it full. The set is already full. So we need to take one of them out, and in place of that, we put the content of the address 6. And of course, it's a mess. So which one to choose? The obvious or the logical choice is we should choose the least recently used. We just used 0 in the previous call or in the previous access. And because of this, we should take out the 8. So we took out the 8, and in place of that, we put the content of the address block 0. And now we have this access, and we looked for it, and unfortunately, it's not there. And because of this, it's a mess. So we take the least recently used, which is the memory 0. We take it out, and instead of it, we put memory 8. So as you can see now, because we moved from the direct map, which is the one-way set associative, to the two-way set associative, we were gaining 1 hit. Now, for the fully associative, you place anywhere because you have a single set. And because of this, you don't have to get any address. Actually, you store anywhere. So what happens for this one? It's a miss, so you write it, mem0. This one, it's a miss, so you write it. Now at 0, it's a hit. Good, we find it. For the 6, we didn't find it, so we write it down, memory of 6. And in 8, we already have it, so it's also a hit. And as you can see, now we have 2 hits because we increased the associativity. Now, the conclusion is increased associativity actually decreases the miss rate. Or what you noticed, we increase the number of hits, which means that the miss rate is going to be reduced. However, it has diminishing returns. To understand this point, we had a simulation of a system with a 64 kilobyte D or data cache, and it has 16 words per block. And we used SPEC 2000, and we are trying to calculate the miss rate. And we choose to do one-way set associative, which is the direct map, two-way, four-way, and eight-way. And we are recording the miss rate. For one-way, the miss rate was 10.3%. And then just by adding one by having two-way set associative, the miss rate was reduced to 8.6%. So that's kind of a big reduction compared to the subsequent reductions. So as you can see, moving to four-way, it was only 8.3%. So the reduction is a little bit low. And moving to eight-way, it's very low. It's just from 8.3 to 8.1%, which is about 0.2% reduction. So as you can see, it's have a diminishing return. So probably you would say that two ways enough, or if you want a little bit more, you would say four-way should be enough for our needs, instead of jumping to eight-way without gaining that much reduction in terms of miss rate. So now we will check the address format, taken into consideration that now we have the other type of caches, which is the set associative caches. So, and to understand this, we are repeating what we've seen before, the tag are compared with the corresponding tag bits in the cache. So we have a tag that is in the address that you want to look for, or whether you want to access. I mean, when we say that you want to access, it means either read or write. So you compare this tag with the tag bits inside the cache. The index is actually used to select the particular set in the cache. The block offset, which is this one, are used to select a particular byte within the block itself. So if you were given a cache size and a block size, and you also supposed to know what is the address width, usually it's from 0 to 31. And MIBS, we know it's from 0 to 31, any address. So if you also were given the cache size and the block size, this is all you need to know what to do with direct map memory, set associative direct map cache, set associative cache, and whatever is the value of n, whether it's two-way set associative, four-way, or and so on. So what you should know for the direct map memory or for the direct map cache, the cache blocks is equal to the cache size divided by the block size. And once you know how many cache blocks you have, then you know how to access or what are the index bits. This one. For a set associative memory, the cache sets, notice that we are looking for how many sets we have. Here we are looking for how many cache blocks we have, since it's direct map. But here we have many sets, unless it's fully associative. If it's fully associative, it's only a single set. So we have cache sets equal to the cache size divided by the set size times the block size. Now, the set size is actually given by how many ways do you want the cache to be? Is it two-way set associative or four-way set associative, and so on? So if it's two-way set associative, then the set size is going to be equal to 2, which means that every set has 2 locations. So you can see the difference here. You divide by the block size if you are direct map cache, and here you divide by the set size times the block size. Now, to get the tag bits at this point, using this equation based on the cache type, you get the index bits. And knowing the block size, you get the offset bits. So getting the index bit and the offset bits, and you know that the total bits is 32, the tag bits is the remaining bits. Now, as an observation, and we will see this in the next slide when we look at the examples, as associativity increases, the index bits decrease and the tag bit increase, which means the more associativity you have, then the bits will move this way. You will gain bits in the tag and you will lose bits from the index. So if you start at two-way set associative, and then you are moving from two-way to four-way set associative, then you will have 1 bit movement this way. You will increase the tag by 1 bit, and you will take out a bit from the index. Notice also, if you have a fully associative cache, so then you don't need any index. The index bit will be 0. So here are 3 examples. If you have a memory address, that is 32 bits. So the address starts from 0 to 31. And the cache size is 512 kilobyte. And the block size is 4 byte. Sometimes we say 1 word. When we say 1 word, it's the same as 4 bytes. So using a direct mapping or using a direct map cache, you look for the cache blocks from this formula that we said, this one. The cache blocks equal to the cache size divided by the block size. And the cache size is 512 KB, and the block size is 4 bytes, which is equal to 2 to the power 19. This is the 512 KB, 2 to the power 19. Remember that the K or the kilo is equal to the power of 10. So we got the 2 to the power 19 because it's actually 2 to the power of 10 times 2 to the power of 10 times 2 to the power of 9. 512 is 2 to the power 9. So you add the exponents, it's going to be 2 to the power of 90. Divided by 4 byte, which is 2 to the power of 2. So from this, if you do this division, you have 2 to the power of 17. And now, since you have this many cache blocks, then you need 17 bits in the index. And you need 2 bits because this is the block size. From the block size, you take the power, and this would be your offset. Your offset is going to be 2 bits. And you will subtract 32 from 17 plus 2. This is 32 minus 19. And this is equal to 13 bits in the tag. Now, we know that the direct map cache is a one-way set associative. Moving to two-way set associative, you will have 2 blocks for every set, or 2 locations for every set. And using the cache set formula, this formula, you actually can use this formula for all the cache types, knowing that the direct map cache set size is equal to 1. So for this formula, we apply it here, and we say that the cache size is 2 to the power 19. This is the same one that we've seen before. Now the set size is equal to 2 to the power of 1, because we have two-way set associative. So this 2 is actually this one, times the block size, which is 2 to the power of 2. This is the same one that we have before. And now we have the cache sets, or number of sets, is 2 to the power of 16. So now know that the index, we know that the index is 16 bits. And the offsets is the same as before, it's 2 bits. And the remaining would be, for the tag, the remaining bits are 14 bits. And you can see that if you noticed the difference between here and here, we actually moved the bits this way. Or we moved this line this way. Adding one more tag to the tag, or one more bits to the tag bits. So now we have bit number 18 in the tags, and we are taking out the 18 actually from the index. And notice that the index were 17 bits in the direct map, and now they are only 16. And this is what we mean by this red arrow that we've said here. This line moved this way. Now, using 4-way set associative, you can quickly get it by moving this one line 1 bit. So instead of the 18 becomes 17, and the 17 becomes 16. And you know that the index are only 15 bits, or you just apply the same equation. The cache set is equal to the cache size divided by the set size times the block size. And the block size didn't change, it's 2 to the power of 2. Now the set size is equal to 4, since we have 4 ways. You can say just 4, copy it directly. And the cache size is the same, 2 to the power 19. If you calculate this, you will end up with 2 to the power of 15, which means that the index bit is 15 bits. And 32 minus 17, which is 15 plus 2, is equal to 50. So now the tags are 50. Also, you could look at what's the trend here. As we are increasing the associativity, the index bits are reduced. If we reach to fully associative, the index bits would be equal to 0. Also, looking at the tag, as we increase the associativity, the number of tag bits will increase. And to see this in another example, if you have a memory address that is only 11 bits. Usually we have 32 bits, but for this example, because I don't have a lot of space in this slide, I assume that the memory address have only 11 bits. And the cache size is 128 byte. It's not kilo anymore, again, for the same reason. I don't have space in this slide. And the block size is equal to 8 bytes. If the address that you are trying to access is this address, then for one-way set associative or the direct map, this is going to be the address subdivision. We know that we have 8 bytes, which is 2 to the power of 3. And this 3 are the 3 bits of the offset. And these are the offset in the one-way set associative, also the two-way set associative, the four-way set associative, and the 8-way set associative. The same offset bits. Now, for the index bits in a direct map, you could divide the cache size by the block size. And you know that this is 2 to the power of 7 divided by 2 to the power of 3, which is equal to the power of 4. So you need 4 bits in the index. And from 11 bits, the remaining bits for the tag is 4 bits. And now we know the observation that we just found. As you increase the ways in the set associativity or in the associativity, this line will move this way. So the index will lose 1 bit and the tag will gain that bit. Similarly here, you move this one. So the index lose another bit and the tag gain that bit. And in an 8-way, the index will lose 1 more bit and the tag will gain that. And if you increase the associativity to 16-way set associative, you will have a single set and you won't have any index bits. So the question was, if the address you are trying to access is this one, now where can you find it inside the cache? In this cache, the direct map cache, since we have 4 index bits, we would have blocks from 0 to 50. While in this one, since we have 3 bits in the index, we would have 8 sets. Now it's 2-way set associative. So we have 8 sets. Since we have 2 bits, we will have 4 sets. 1 bit, then it is 2 sets. Now, one quick way to know exactly how we get this figure, we get different addresses and we locate them inside the cache in the direct map. And we say that location 0, if the address is 0, it would be here, followed by 1, 2, 3, until we reach to 15. And then we continue from the top, 16, 17, 18, and so on. And then we continue 32 and so on, up to 47. And then we continue 48, and so on. Similarly for this one, we start from 0 to 7, and then 8, going down to 15, and so on. And now you know how do we get these numbers. However, you don't actually need them. You can get it from the binary address directly. Now you know that these 4 bits are the index. And in the index, this is the 4 bits that we are seeing here. Actually, I copied this address here. So this is 9. And we go to block 9. For the 2-way set associative, we found that this is 1. and we go to set 1. For the four-way set associative, the index is 1 also, so we go to set 1. And for the 8-way set associative, the index is 1, so we go to set 1. Now notice for each set, in a direct map, you have only one location or one place for all the place inside the cache for this block. While in two-way set associative, you have 2 locations. In 4-way, you have 4 locations or 4 ways. And in 8 ways, you have 8 different locations. Now, this is another example. This is a set associative cache organization where you have a 4-way set associative. You have 4 KB cache with 1 word per clock. 1 word per clock. This means that you have 4 bytes inside each block, which means that you need 2 bits in the offset, and these are the 2 bits. Now, since you know the cache size and the block size, you can get the index bits, which is 4KB divided by the block size. Let me take this out, which is 4 bytes or 1 word. And if you made this division, you will notice that 4K is 2 to the power of 12. And 4 byte is 2 to the power of 2. However, this is true if it is a direct map. We said here that this is a 4-way set associative. And because of this, we need to multiply it by the number of sets, which is, the number of ways, which is 4. So we multiply this by 4, which is 2 to the power of 2. So now you get 2 to the power of 12 divided by 2 to the power of 4, and you subtract the exponents, and you get the result equal to 2 to the power of 8. And from this, you know now that you have 8 bits in the index. And the remaining bits for the tag is 32 bits, the full address, minus 8 minus 2, which is equal to 22. Now, what happens if you access the cache? You get the index from these 8 bits. And since you have 8 bits, you have 2 to the power of 8, which is 256 location from 0 to 255. And you choose the one that is indicated by the index bits. For example, this is the one. And now, since this is 4-way, you will have 4 different entries or 4 different locations for every set. Now, to know if you have a hit, you check the tag against every tag in the 4 ways. And you also check the valid bit for each one of them. So if you have a valid bit and the tag is the same as the tag inside the address, then you have a hit. So let's say that our data was here. And let's say, suppose that all the locations have valid bits equal to 1. So this is equal to 1. here is equal to 1, which means that there is a data there, and here is 1, and here is also 1. But when you compare the tag to this tag, they are not the same, so it gives you 0. Similarly, when you compare this tag, it gives you 0. Now we know that this is the one that we want, and the tag matches the tag in the address, so this gives you 1. 1 ANDed with 1 will give you 1 in this line. And here it's 0. So you notice that the results after the AND gates, or the output of the AND gates, are 0, 0, 1, 0. And you are ORing these lines. So whenever one of them is hit, then you have a hit. Now, you know that you get the hit from this one. So you need to supply the data outside. And to do this, you need 4-to-1 multiplexer. The selector lines for this 4-to-1 multiplexer is using one-hot encoding. You know, if you have 4-to-1 multiplexer, you need 2 selector lines. However, there is another way to do this using one-hot encoding, and we have it here. Notice that we have 0 and 0 and 1 and 0. So you give this code as selectors to the 4-to-1 multiplexer, and this will supply the this entry or this location or these data. So you get the data from here, and you get it in the data line outside the cache. Now, for a replacement policy, we've mentioned that in direct map, there is no choice. You have only one choice. Either you get the data, if it's the data that you are seeking, or you overwrite it by the new data. In a set associative, you have a choice when you are replacing or when you need to write something new to the set that you already picked. So you prefer non-valid entry first. If there is an entry that's empty, which means that the valid bit for it is equal to 0, pick that one since it's empty and put the new value there. Otherwise, choose among the entries in the set. And this happens if the set is full with entries. At this point, you have 2 choices. One of them is kind of logical, and it looks logical to me as well, which is the least recently used. So if you have, for example, 4-way set associative, you have 4 contents already stored, or 4 entries that are full with data with valid bit is equal to 1. So you choose the one that you didn't access the longest, which is the least recently used one. You take it out and you replace it by the new. So you choose the one unused for the longest time. This is simple for 2-way, manageable for 4-way. It's a little bit too hard beyond that, because you need to have certain way to know which one is recently used and which one is the least recently used. You need, for 2 ways, it's easy. 1 bit can't tell you this. If it is 4-way, then you need 2 bits to know exactly which one is the least recently used, and so on. Another way is randomly you pick one of the entries. So it gives approximately the same performance as the least recently used for high associativity. So if your associativity is high, and by high we say 16-way or 32-way is kind of high. So if that's your cache, then don't worry about the least recently used anymore. Just pick it randomly, and that's it. You will get about the same performance. Now, for a multi-level caches, you have the primary level 1 cache attached to the CPU. As you can see here, we have a core system, and this core we have a CPU maybe with multiple cores. One of the cores have its registers close to it, and then you have the primary level 1 cache here. It's usually split into instruction cache and data cache, and these caches are small but fast. Now, following this, we have level 2 cache. Usually this is unified between the instruction and the data. And it's larger, but slower than the level 1 cache. However, it's faster than the next levels. It's faster than the level 3 cache and the main memory. And its job is to surface the misses from the upper level. So if you have a miss from level 1 cache, you would find it in the, hopefully you will find it in level 2 cache. Level 3 cache is also unified between the instruction and the data, and is actually shared between different cores. If you have multiple cores, so level 3 is shared between all of them. Level 2 is private to each core, usual. Now, it's larger and slower. Again, it's larger than level 2 cache, but slower than it, but faster than the main memory. And it serves the misses from any upper level. So let's say that you're trying to find the result in the register, you didn't find it, you go to the cache, you didn't find it, you level 1 cache, you didn't find it, you go to level 2 cache, and if also you didn't find it, then you go to level 3 cache, which means that level 3 cache served all of the upper levels. For the main memory, this is the largest and the slowest, and serves the misses from all the upper levels. Now, we do this because we want to gain the advantage of both worlds. We want a large memory and at the same time, fast. And to understand this, here's an example. This is a multi-level cache example, but at the beginning, you have the CPU-based CBI equal to 1. I'm trying to organize the given information in a table. So you're given the CPU-based CBI equal to 1, the clock rate equal to 4 gigahertz. The level 1 cache miss rate is 2%. So that's the miss rate. And the main memory access time is 100 nanoseconds. This is actually contributes to the penalty. So that if you are accessing the main memory, this means that you already missed the information. It's not in level 1 cache. So you go to the main memory. And in this example, we have only level 1 cache followed by the main memory. So there is no level 2 and no level 3. Now we need to get the level 1 cache miss penalty in terms of cycles. And to get this, we have 100 nanosecond. This is the access time for the memory. And you access the memory only if you have a miss. If you have a hit, then you just get it from the cache and that's it. So it's 100 nanosecond divided by what's the time for a single cycle. And the time for the single cycle is given by the clock rate, which is 1 over 4 giga. And 1 over 4 giga is 0.25 nanosecond. So you divide the 100 nanosecond divided by the time for one cycle, which is 0.25 nanosecond. And that's 400 cycles. And that's a lot of cycles. If you are accessing the main memory, then the level 1 cache miss penalty, it's paying 400 cycles in case you missed from the level 1 cache. And this way you need to go to the main memory. So now the effective CBI is actually 1, which is the base CBI or the ideal CBI, plus the miss rate. We have only 2% of the time we are having a miss. So it's 2% times the miss penalty. Notice that the miss rate always goes with the miss penalty. They are multiplied by each other. So 2% times 400, and then you add 1 to that, then you have the effective CBI equal to 9. And we record this in our table. So you know now we have 400 cycles as a miss penalty and 9 as the effective CBI. Now we will introduce the level 2 cache to the system, hoping to reduce the effective CBI. If we say that the level 2 cache access time is 5 nanoseconds, notice that it's much less than the main memory access time, which is 100 nanosecond. L2, it takes only 5 nanoseconds because it's smaller in size and it's also faster. Now, if we assume that the level 2 cache miss rate is 25%. So the miss rate here is 25%. The primary L1 cache miss followed by a level 2 cache hit will have this penalty. And this happens if you hit from level 1 cache, that's it, you're done. You will have the same base CPI. But if level 1 cache miss and you find the information in the newly added level 2 cache, it was a hit, then the miss penalty is the access time of the level 2 cache only, which is the 5 nanosecond divided by the 0.25 nanosecond. This is the time for a single cycle. So we have 20 cycle as a miss penalty for accessing the level 2 cache. And this is what we recorded here. Now, if you had a miss in level 1 cache and you looked for it in level 2 cache and it's also a miss, then what's the penalty? The penalty is you have to go to the memory, the main memory. And you know that the main memory take 100 nanoseconds, and we already found out that it takes 400 cycles in the previous question. So why the miss penalty is 420 and not only 400? Because what happens is you went to level 1 cache first and it was a miss. And then you went to level 2 cache and this takes 20 cycles from you. And it's also a miss. And because of this, you will spend 400 cycles more in the main memory. So you add 20 plus 400, and this is 420 cycles. And at this point, you can calculate the effective CPI, which is 1, the ideal, plus 2%, which is the miss rate of the level 1 cache, times the cycles that you will pay, your penalty. If you find it, if you didn't find it at level 1 and you find it at level 2 cache. So that's 20. Plus, if you missed it in level 1 cache, so this is the miss rate of level 1 cache, and you also miss it in level 2 cache, and that's the miss rate of the level 2 cache, which is the 25%, times how many cycles you are going to spend, which is the 420. And if you calculate this, you'll find that it's equal to 3.5. Now, comparing the 3.5, which is the effective CPI, by adding the new level 2 cache to the previous case, when you have only level 1 cache, you know that the CPI here is a lot, which is 9, while here it's only 3.5, which means that you gain the speed up of 2.6. If you find the performance ratio, so you divide the bigger number, which is 9, divided by 3.5. So this system where you have level 1 cache, followed by level 2 cache, followed by the main memory, have gained you a lot of speed up, which is 2.6. So it's 2.6 times better than the previous setup. As a side note, notice that we have the level 1 cache local miss rate, and that's 2%. We also have the level 2 cache local miss rate, which is the 25%. If you want to get the level 2 cache global miss rate, which means that you already missed the level 1 cache, and you also missed the level 2 cache, and you went to the main memory, then that's actually the 2% multiplied by the 25%. which is the purple term here. So 2% times 25% is actually 0.5%, and this is called the level 2 cache global miss rate. So now we have the following multi-level cache considerations. The primary cache focuses on the minimal hit time. Level 2 cache focus on how or on low miss rate, or how to reduce the miss rate to avoid the main memory access. The hit time has less overall impact if you use level 2 cache. The result, level 1 cache usually smaller than a single cache, which means that if you used two levels, level 1 and level 2, this is better for you. Also, level 1 block size usually smaller than the level 2 block size. To understand these 2 points, if you use only a single cache, then usually, and let's compare this against level 1 and level 2. So this is only level 1 cache. And this is the system where you have level 1 followed by level 2. And this system, if you looked at this system, level 1 cache usually have smaller size than if you use only level 1 cache. Also, level 1 block size smaller than the level 2 block size. So if you compare the level 1 against level 2, you'll find that the block size here is smaller than level 2 block size. And this is following the hierarchy that we explained before. Now, this is the big picture. So the memory hierarchy, the common principle apply to all levels of the memory hierarchy based on notions of caching. At each level in the hierarchy, you should know those 4 information. The block placement, finding a block. Block placement means that where do you put the block? Finding a block means if there are blocks inside the cache, how to find the block that you want. Replacement on a miss, and that's the case when you don't find the information that or the data that you want in the cache, and the set or the cache is already filled. So what should you take out? Which one of the blocks you should take it out and get your new block in? So that's what we call the replacement. So how to do the replacement? And we've talked about this quickly when we said least recently used. Also, the right policy. So we will have a quick revision on these 4 points, each one of them in a slide by itself. So for the block placement, it's determined actually by the associativity. The direct map, which is one-way associative, you have one choice for the placement. The n-way set associative, you will have n choices within the set. The fully associative, you can place it in any location, you can place the block. The higher associativity actually reduces the miss rate, as we find, but this is not for free. This increases the complexity, the cost, and the access time a little bit, because you will probably need multiplexers. You need to look for the blocks or search for them in many locations. Now, finding the block, it depends on the cache type. If it is direct map, you find it directly by looking at the index, and it tells you exactly where is it, and you compare only a single comparison. You compare the tag to the address. For the n-way set associative, you have a set index, and then you need to search the entries within the set, which means that you need to do n comparisons. Now, the fully associative, you need to search all the entries. It's like a full lookup table. And the tag comparison If you search all the entries, you need to search all of them. If it is a full lookup table, then you don't need to do this, but you need to have the knowledge of building the lookup table correctly. As a hardware note, the hardware of the implementation of the cache in hardware, you reduce the comparison to reduce the cost. Now for the replacement, this is two choices. The choice of an entry to replace on a miss, either you use the least recently used or you take it as random. The least recently used is complex, and you need to have a way to know which entry is used more than the other, which one is the least recently used, which one is the most recently used, and based on this, you need to do some hardware, or you need to add some hardware. For the random, it's close to the least recently used and easier to implement, especially if the associativity is higher. Now, for the write policy, you either do a write through or a write back. The write through, you update both the upper and lower level, and this simplifies the replacement, but may requires a write buffer. Otherwise, you will take a lot of time accessing the lower level storage. In the write back, you update the upper levels only and update the lower level when the block is replaced. And this is why we use the dirty bits. To keep, also you need to keep you need to keep it more stable. Or I mean, you need to keep more states to make sure that you do the write back correctly. Now, the sources of the misses, we have three sources, and we call them the 3 C's: the compulsory misses, the capacity misses, and the conflict misses. The compulsory misses, also known as the cold start misses, this is when you first access, when you have a first access to a certain block. You have a compulsory miss. There you must miss. Also, if they you just started the system and the cache is empty, all the valid bits are equal to 0. At this point, it's compulsory misses. The capacity misses, it's due to finite cache size. Because you have a finite cache size, you will get a capacity miss. Otherwise, if you have more capacity, you won't have this miss. A replaced block is later accessed again. This contributes to the capacity misses as well. The conflict misses, or it's the collision misses, this is in a non-fully associative cache, meaning in the direct cache or the direct map cache or the set associative caches. You have a conflict miss due to the competition for the entries in the set. So there is a space in the cache, but you cannot access this space because you are limited within a set or within a block. And this is why we call it a conflict misses. And would not occur if in a fully associative cache of the same total size, because you have the spaces, and you will never have a conflict miss. If the fully associative cache is completely full, then this would be a capacity miss. Now, the cache design trade-off, if you want to increase the cache size, the effect on the miss rate, it will decrease the capacity misses, but the negative performance effect, it may increase the access time. Now, for increasing the associativity, it will decrease the conflict misses, because you are having more location in every set. But it may increase the access time as well. Increasing the block size decrease the compulsory misses, but increase the miss penalty, since the block size is now bigger. For very large block size, it may increase the miss rate as well due to pollution. Now, we are moving to the cache control. And this is actually it's like a revision to what we've studied so far. So this is an example cache characteristic. You have a direct map cache with write back and write allocate. The block size is 4 words, which is 16 bytes. And the cache size is 16 kilobytes, which is a 1024 blocks. So to get the breakdown, since you have 4 words, the offsets are 4 bits. The offset is 4 bits, because 16 bytes is 2 to the power of 4, and these 4 is the 4 in the power is there, represented by 4 bits in the offset. Now the cache size is 16 kilobyte, and you want the index bits. Since this is a direct map cache, you would say that my cache size is 2 to the power 14 divided by my block size, which is 2 to the power of 4. And this is equal to the 2 to the power of 10. So you take the 10 and you know that this is the number of bits in the index. And the remaining bits would be the tag bits. You also have a valid bit and a dirty bit per block. The valid bit we know why, to know if the contents is valid or it doesn't have any. The dirty bit, because you use the write back method or technique, then you need to use dirty bit. And we have a dirty bit for every block. We have also a blocking cache, which means that the CPU waits until the access is complete. Now, this is the interface between the CPU or the processor going to the cache, and from the cache going to the memory. Notice that the addresses, you have controls like read and write, moving from the CPU to the cache and from the cache to the memory. So this control is repeated here. And also the valid and the ready signal. When the cache is ready, it tells the CPU it's ready, and the CPU can access. If the memory is ready, it tells the cache is ready when the cache wants to have something from the memory, or also when the CPU wants anything from the memory. So these are the controls. Now looking at the data path, the address is 32-bit. So you need to move the address to the cache, and also from the cache to the memory, you need to have 32-bit. Now for the data, we have the communication between the CPU and the cache in 32 bits. And the reason is because we know that every instruction is 32 bits and every data is 32 bits. So when you write data into the cache, it has to be 32 bits. If you want to something from the cache, you want to read the data from the cache to the CPU, then you need also 32 bits. Now, the interaction between the cache and the memory, we said that it is 4 words, or the block size is 4 words. So the movement from the cache to the memory and vice versa, it has to be in 4 words. And 4 words is actually equal to 2 to the power of 2 times 4 word equal to 2 to the power of 2 times 2 to the power, and 1 word is 32, so it's 2 to the power of 5 and the total is 2 to the power of 7, and that is 128 bits. And this is why we have this bus. Also, it's multiple cycle per access when you access the memory. If you access the cache, you get it directly, but for the memory, you will have penalty, which is a lot of cycles. Now we want to get the finite state machine that controls the cache. So as a quick introduction, even though we've taken this in the revision, we are saying this again, that the finite state machine, you use the finite state machine to sequence the control steps. As you can see here, you have the combinational logic. Now, from the cache point of view, you will get the inputs from the cache data path, and the outputs will be going to the data path control outputs. And you will have next state going to a state registers based on the finite state machine that you are going to develop. You will have certain number of D flip-flops here, and then you will supply the present state along with the inputs to have a general inputs to the combinational control logic. So you have set of state transition in each clock edge. The state values are binary encoded, and the current state stored in the register, which is this state register. Now, the next state function, which is the function that you need to find here, is a function of the current state and the current inputs. So to find this, you need both of them. Now, the control output signal, which are these outputs. So these outputs are a function of only the current state. And this is actually the Moore model. This is the Moore model. Now, the cache control finite state machine, in a simple way, we draw the states this way. So this is the ideal state. If you have a valid CPU request, you go to this state, which we call compare tag. And this is what the job that you usually do. If you compare the tag and it's a hit, if in case of a cache hit, you mark the cache ready and go back to idle. And this is what we've seen here inside the state. If it's valid and it's a hit, then you set the valid and you set the tag. And if the write, if you are doing the write, then in the location, you should set also the dirty bit. So you should worry about the valid, the tag, and the dirty bit. The valid and the tag, you set them directly. The dirty only if you are writing. Now, if you are in this state, in compare tag, and you found that you have a cache miss, there are two ways. Either you have a cache miss and the block that you want to replace is clean, or the old block is clean. At this point, you go to this state, which we call it allocate. And you know, in allocation, you need to fetch the block back to the cache. So you read the new block from the memory and bring it back. As long as you need more time to finish this operation, if the memory is not ready, keep waiting in this state. Once the memory is ready and you're done, then the memory is ready and you go back to this stage or to this state. Now, if you have a cache miss and the old block is dirty, this means that first you need to do a write back. And once you're done with the write back, you go and allocate, which means that you fetch the block back to the cache. So in case you are writing back, as long as you are in this process, the memory is not ready and you are waiting in this state. Once you're done, you say that the memory is ready and go directly here. And notice that this in a very short amount of time, because you'll say memory is ready, go to allocate. And the moment you go to allocate, the memory is no longer ready. It's not ready, so you keep waiting until it becomes ready and you fetch the block back to the cache. So these are the cache controller, finite state machine. And this state actually, since it do many jobs, it could be partitioned into separate states to reduce the clock cycle time. And we reach to the dependable memory hierarchy and the subject of dependability, but we will leave this to the next video.